Okay.
So it's a pleasure to introduce Santiago Ramírez from Universidad de Buenos Aires. He will talk about decomposition theorems for involutive solution to the Yang-Baxter equation. Thank you, Santiago.
Okay. Thank you, Monique, for the introduction, and thank the organizer for the invitation and everyone for listening to the talk. So I talk about some decomposition results for involutive solutions to the Yang-Baxter equation. This is joint work with Leandro Bendramin and part of my work towards my PhD. And so usually one is interested in, or at least originally one is interested in linear solutions to Yang-Baxter equation. But Drinfeld, I think in the early 90s or late 80s, proposed studying set theoretical solutions, which are essentially solutions that are act by permuting elements of a basis, which should be in some sense simpler solutions of the Yang-Baxter equation. And so since then, one studies this set theoretical solutions. So I'll repeat a little bit of what Emiliano said before. So a set theoretical solution of the Yang-Baxter equation is a set X with a bijective map from the Cartesian product of X with itself to the Cartesian product such that the following equation holds. So here R12 is the map R acting on the first two components of the threefold product of X. And so this is an equation for functions on the threefold product of X to itself. And this is technically the braid equation. We probably recognize it like that. But the Yang-Baxter equation and the braid equation are equivalent in the sense that we have explicit bijections between solutions. And it's standard to work in this form of what would be called braid equation. Okay. So one usually writes for the map R, for the components of the map R, sigma x of y and tau y of x. The idea is as if one is thinking about essentially the twist, exchanging x and y, and then further acting by some permutations that might depend on x or y. This need not be the case for general solutions, but we will, for us, the solution will mean a non-degenerate solution. So, like Emiliano said in his talk, sigma x, all sigma x's and tau x's are permutations or projective functions. So one can think of this in these terms. And we will also focus, for us, all solutions will be involutive. Okay, so they will satisfy R squared equals the identity function. So one would hopefully like to classify solutions to a Yang-Baxter equation or somehow understand them. Of course, if one computes the solutions for small sizes, so non-isomorphic solutions of size up to 10, we get the following. So for size 10, we already have like 5 million solutions. So any sort of explicit classification of solutions is not likely going to happen. So one should then care about understanding them in some other way. So one way of understanding them is what Emiliano talked about, is talking about retractions of solutions and interpretation solutions. But another very natural definition and sort of approach to this problem of understanding the solutions is defining what are known as indecomposable solutions. So we say that the solution is indecomposable if we cannot write it as a disjoint union of two subsets in such a way that we can restrict the R map to these subsets. So in that case, we say a solution is indecomposable. And so one might try to classify all indecomposable solutions and then see if one can find the different possible ways of sort of gluing solutions to build solutions of bigger size. And if one checks how many indecomposable solutions are there for the sizes that we know how many solutions are there, we do indeed get something that's quite more manageable than what we had before. And so such a classification might be more likely than a general sort of classification. And I want to comment that solutions up to size 8 were computed by Edinghoff, Shedler, and Soloviev in 1999. But solution size 9 and 10 are actually recent work, quite recent, of Vendramin, Merev, and Akgun. And quite recent is last year or the previous year, I'm not sure. Using some techniques of constrained programming. But it's quite hard to compute these solutions in general. Okay, so part of the reason of restricting to non-degenerate and involutive solutions is what Emiliano was talking about, which is we get interesting algebraic tools for studying these solutions. So we will define the structure group of a solution and the permutation group of a solution. So the structure group of a solution is the group generated by the elements of the set, with relations given by essentially acting by the R map. So the product of a pair XY, we set it to be equal to the product of R of the pair XY. And the permutation group is simply the group generated by the sigma X maps as a subgroup of the symmetric group on X. So the sigma map that sends an X to the sigma X actually extends to an action of this structure group. So this permutation group is essentially just the image of this action by the map. Okay. So for many purposes, it might be interchangeable to talk about either the structure group or the permutation group in terms of the action. They are pretty much equivalent, but we will talk about the permutation group because this is a finite group in contrast with the structure group, which need not be finite, in general will not be finite. So one then tries to study solutions in terms of this action. And so indecomposable solutions can be characterized as those for which the action is transitive. Okay, so, and when one tries to further use these ideas to understand solutions, a result of Edinghoff, Shedler, and Soloviev, which is what might stand out first to the eye when you saw the table before, which was at the primes, we had just one non-isomorphic or isomorphism class of solutions. This is a result of Edinghoff, Shedler, and Soloviev, which is if P is a prime number, there's just one solution of size P up to isomorphism. And this is actually explicit. In order to build a solution, you just have to grab a single cycle of length P and set all sigma x's to this cycle and all tau y's to the inverse cycle. And if we further restrict the action to be a bit more than transitive and or quite a bit more than transitive to be primitive, we have a recent result of Sedoy, Jespers, and Okninsky, which says that actually up to isomorphisms, the only primitive solutions are the indecomposable solutions of prime size. So these are the only primitive solutions of any size are the indecomposable solutions of prime size. So there are no more primitive solutions. And this answered the question of Ballester-Bolinches. And again, this is quite recent work for last year. In fact, I'm not sure it's on the archive, but I'm not sure it's published yet. So we'll give an example. We set X, the set with 6 elements, and we give R by the following maps. We set the sigmas and the taus as we see here. And the solution defined by this is in fact decomposable. Of course, it's not necessarily obvious from presenting it like this, but a way to sort of visualize the solutions a bit better is by building a matrix which has as rows the tau maps essentially. So we have actually tau inverse of tau 1 inverse of 1 is this first entry. Then we have tau 1 inverse of 2 and so on. As the rows, we have the tau inverse maps. And this turns out to be a good way of understanding solutions, and finding a decomposition of a solution is essentially equivalent to finding two submatrices of complementary submatrices inside this matrix. This is not obvious at all, because in principle, we're just looking at the tau maps with this thing, and we're not saying anything about the sigmas. But it turns out that for involutive solutions, this turns out to be the multiplication table for an algebraic structure with a single binary operation known as a cycle set introduced by Rump in 2005 that is equivalent to involutive solutions. So it's the same to giving one of the cycle sets or an involutive solution. And these properties of solutions can be read from this in this way. And so now to the sort of results that we're interested in. In 1996, during a talk at the International Algebra Conference, Gateva Ivanova conjectured that all the so-called square-free solutions were decomposable. Now, I'm not sure what was exactly the original statement of the conjecture, because Gateva Ivanova was, as I understand, interested more in studying some monoids generated by solutions, and not so much on the solutions. But in the paper in 1999, Ettinghoff, Shelder, and Soloviev defined this function T of x, which is in this way for a solution. And they noted that square-free solutions are exactly the ones satisfying that this T map is the identity. And so they check Gateva Ivanova conjecture for all solutions up to size 8, which were the ones they had computed. And one very surprising fact about this T map, which is very relevant, is that it's actually a permutation. Again, it's not obvious at all that this would end up being a permutation on X, but it is a bijective map. And so the conjecture was eventually proved by Rump in 2005. So this is the same paper in which he introduced the cycle set structure. So these are the sort of results that we were interested in. Oh, before that, going back to the example that we had before, we can read this T map from the diagonal of the matrix. So again, it turns out to be a very convenient way of sort of packing all the information for involutive solutions. This matrix for the cycle set. This can the T function can be then read from the diagonal map, so we can see that this is the same example we had before, and it's actually a square-free solution. So as we said before, this is a decomposable solution. And furthermore, since it's square-free, every subsolution will also be square-free. And so these subsolutions will again be decomposable. So we can find, again, new submatrices inside these ones that decompose the subsolutions. So these are the sort of results that we were interested in with Leandro. So we wanted to see if we could, what could be said about decomposability or indecomposability of solutions in terms of the cyclic structure of this T permutation that we have here, this T function. And we refer to this cyclic structure as the T invariant of the solution. So the first sort of result in this direction that one can get is relatively straightforward, which is that we had the result of Rump, which said that if the T is the identity function, so this very degenerate case in which it's a trivial permutation, the solution is decomposable. And if we go to the sort of opposite extreme, in which the T map, this T invariant, is a cycle of maximal length, then one gets that the solution has to be indecomposable. And this follows from the following result, which is pretty clear if one thinks in terms of the matrix. Again, we won't be able to find any sort of complementary submatrices if already the diagonal can be broken up in any way. So more interesting is probably the following result. If we make this T map sort of a bit shorter and its rather than a cycle of length n, a cycle of length n-1, then we can show the solution has to be decomposable. Now, the first problem that one has with trying to find this sort of result is that there's in principle, there's a sort of a priori no connection between this T invariant and the group action, in the sense that this T permutation need not be an element of this permutation group, or there's no reason one would expect that any conjugate is an element of this permutation group. So it's sort of difficult to say anything about the action if we know the T function. But in the special case in which one has a fixed point for this T map, then we were able to actually actually connect this T map with the action of the group, more concretely with the sigmas that are labeled by these fixed points of the T function. So concretely, we have the following result. So if x is a fixed point of the T map, then for every y, the following equation holds. Now, this doesn't look particularly nice, but this is a situation in which the notation is sort of working against us. So for us, x will be some fixed element, and y is the one that's free to move. So one should think of these things as functions of y and not of x, which is what the notation might be implying in this way. So if one sets tau y of x to be some sort of f of y, then this equation reads T of f of y is equal to f of sigma x of y. So if this f map were a bijection, that would be saying that this T function and the sigma x are conjugate elements of this metric group. And we would have what we said we in general don't have, which is that the T actually does belong, or at least some conjugate of the T belongs to the permutation group. However, this is generally not the case. This F map will not be a permutation. In fact, this F map is sort of like looking at the columns of the matrix that we had before. And if you recall how that matrix looked, the columns were very far from being permutations. So that's not going to be the case. But in the particular cases that we looked at, this thing was sort of enough to prove what we wanted. So for this case of a cycle of length n-1, if we grab x its only fixed point, one can show that this sigma x must also be a cycle of length n-1. Once one has that, it's relatively straightforward, at least in this case of a cycle of length n-1, to show that the action of the permutation group, if it were transitive, it would also be permutive. And so this contradicts the result of Sedoi, Jespers, and Oglinski, and we can't have then such a transitive solution. Okay, but moreover, one can prove sort of the following. So if we keep sort of shortening this cycle, we still can say sort of this kind of results about the decomposability of the solution. So if we have a solution of size n and this cycle of length n-I with I equals 1, 2, or 3, and let's say a little bit more about why it's stated in this way. We need to ask further that the size of this cycle and the size of the solution be co-prime, but we can again conclude that the solution has to be decomposable. So in here we can't conclude something as strong as saying that the sigma x should be a cycle of the same length, but what one can say is that there is some fixed point. This need not hold for every fixed point of T a priori, but there is some fixed point of this T map whose cyclic structure or satisfies that the cyclic structure of the sigma x will contain some cycle of length n-I. Okay, and this can be said like much more generally. We don't really require this 1, 2, 3 here. So this statement is sort of much more general, but we can also but to finish up the proof and show that the action would need to be primitive, we need some ad hoc arguments that do depend on this 2 and 3. So we do believe that the following should hold sort of in general, which is that if X the solution of size n and this cycle of length n minus I, with this cycle should be at least half of the size of the solution and co-prime with the size of the solution. The next should be decomposable. And we do think that sort of the same kind of arguments or methods, one should be able to prove this, but we haven't found quite the correct sort of general argument. One can keep going with sort of ad hoc arguments for sort of bigger values for I, or one can make this. So if we ask that the size of the solution be co-prime not just with I, but with I factorial, so with every number that's less than or equal to I, then one can conclude decomposability. But we can't find the right argument to include that this statement should hold. But we do believe that this should actually hold in general. And so we actually believe that much more should be able to hold, because if we, I will finish up by showing this table that has the cyclic structure, so the T invariant for all indecomposable solutions of size up to 10. But what one sees here is that the cyclic structures seem to be quite restricted. So there's a lot of things that don't show up here, say, in some way. So we don't see many sort of functions of T invariants with fixed points, or we don't see actually any cycle that is co-prime to the size of the solution. And by this, I don't mean that the T is a cycle co-prime to the solution, but none of these T's has any cycle that's co-prime to the size of the solution. It's in the cyclic structure, right? So we do believe that there should be sort of more general results of this sort, relating, sort of restricting the T invariant for indecomposable solutions, and we're working, trying to work in that direction, and that's all I wanted to talk today. So thank you for listening.